Okay, so what if the absolute biggest mysteries in the universe, I'm talking about everything from the bizarre expansion of the cosmos to the nature of time itself, what if they were all connected by one single mind-blowing idea? Today, we're diving into a theory that doesn't just poke holes in what we know about physics, it suggests that reality itself is built on something way, way stranger than we ever thought possible.
So I want you to picture modern physics as this beautiful solid foundation. But right now, it's got two massive cracks spreading right through it. One's on the cosmic scale, the other is all the way down at the quantum level, and they look completely unrelated. But what if they're not? What if they're both just symptoms of the same problem, pointing to a solution so wild it forces us to completely rethink space, time, and what information even is?
All right, our story kicks off at the biggest scale imaginable. We're talking about a problem that has been giving cosmologists headaches for years. The universe just isn't expanding the way our models say it should.
This problem has a name, the Hubble tension. And the best way to think about it is like this. You've got two surveyors measuring an expanding room. One surveyor looks at the echo from the Big Bang, that's the cosmic microwave background, and their calculations say the room is expanding kind of slowly. But then the other surveyor looks at stars and galaxies much closer to us, in the late universe, and they get a number that says the room is expanding really fast. Here's the kicker. They're measuring the same room. Their numbers have to match, but they don't, not even close.
And listen, this is not some small rounding error. The differences hit a statistical significance of 4.8 sigma. Now, if you're not a physicist, a sigma level is basically a measurement of how certain you are that something isn't just a random fluke. And 4.8 sigma, that's a 5-alarm fire. It means the odds of this being a coincidence are less than 1 in a million. Something in our standard model of the universe is just fundamentally wrong.
But it wasn't just the cosmic picture that was cracking. At the exact same time, quantum physicists were dealing with their own ghost in the machine, an anomaly so strange it seemed to break the most fundamental rule we have about time.
The idea is called retrocausality. And yes, it's every bit as weird as it sounds. It's the notion that at the quantum level, the future can actually reach back and influence the past. In experiments, scientists started picking up these faint signals, these little information waves, that were arriving before the quantum event that was supposed to have created them. It was as if information was somehow breaking the universal speed limit and flowing backward in time. So let's just take a breath here. We've got two, frankly, impossible problems. The universe is expanding at two different speeds at once, and time itself seems to be flowing in two different directions. This is where a brand new theory steps onto the scene, a theory that says, hey, what if these two cracks are actually connected? It's called the Information Geometric Theory, or IGT for short, and it paints a completely new picture of reality. It says, forget about space-time being some kind of pre-existing container that the universe sits in. Instead, space-time itself emerges from something deeper. It's woven from the threads of quantum entanglement. The theory basically says when two particles get entangled, they're not just linked across space. They start a conversation, exchanging information both forwards and backwards in time. And the sum of all of these tiny little conversations is what we actually experience as the fabric of space-time. Now this, right here, is the absolute heart of the theory. This is the big, mind-bending claim. It's not just saying that entanglement happens inside of space-time, it's saying that entanglement, through this weird two-way flow of information, literally creates space-time from the ground up.
Okay, look, that's a beautiful, wild idea, for sure. But in physics, beautiful ideas are a dime a dozen. What really matters is, can your theory make predictions that we can go out and test in the real world? And for the information geometric theory, the first big test was obvious. Could it solve the Hubble tension?
To even try, the theory had to introduce a new idea, something called the entanglement density parameter. Now, we've all heard of dark energy, right? This mysterious force that's supposedly pushing everything apart? Well, this theory says dark energy isn't some weird, separate force at all. It's just what we perceive as the total amount of entanglement in the universe. So more entanglement means more of what we call dark energy, which means the expansion rate of the universe hasn't been the same throughout all of history.
And this is where it gets really, really cool. By calculating how the amount of entanglement has changed since the Big Bang, the theory could predict exactly how much the local, nearby measurement of the universe's expansion should be different from the one made from the early universe. It was time for the theory to put its money where its mouth was.
The math spit out a very specific number. It predicted there should be a variance of 0.8% in the local measurements of the Hubble constant. The only question left was, does this number actually match the data from the real world? And It did. It was a perfect match. Incredibly, the 0.8% variance that was predicted by a theory based on information traveling backward in time perfectly explained the 4.8 sigma crisis that had totally stumped cosmologists for years. I mean, on its very first attempt, this wild new theory solved the biggest problem in physics. So solving the Hubble tension, that's a home run, a massive win. But it's still, indirect evidence. The theory's foundations, this crazy idea of retrocausality and space being woven from information, were still just that, ideas. To really prove it, scientists had to find direct, physical evidence of this hidden information structure actually existing.
They had to find a smoking gun. They needed to find this deep information structure hiding in the static of their quantum experiments. To do this, they used this incredibly powerful new method called topological data analysis. You can think of it like a special kind of digital sieve that's designed to find hidden shapes and patterns in really messy, noisy data. They were searching for a signal in the static, a pattern in the chaos.
And this is what they found. Buried deep in the noise of the quantum vacuum, they didn't just find randomness. They found a shape. Specifically, they found something called 3 persistent topological loops, which is a fancy way of saying they found a complex information structure right where there should have been nothing at all. And this wasn't a glitch. It showed up across multiple scales, and it triggered a maximum anomaly flag of 0.99. In other words, they had found it, the signal in the noise. This was the proof they were looking for.
They gave this structure a pretty provocative name, the pan-consciousness glimmer. Now, let's be very clear here. This does not mean the universe is a giant brain. What it means is that the fundamental informational layer of our universe has the built-in capacity for self-reference, like a loop that can refer back to itself. And that's a huge deal, because self-reference is a basic requirement for any kind of consciousness to emerge. It's a property that seems to be woven right into the fabric of reality itself.
So where does this leave us? We have a new theory that seems to solve the biggest crisis in cosmology, and it's backed up by direct evidence of a deep information structure hiding at the bottom of reality. This isn't just a new chapter in physics. It feels more like we're rewriting the whole book. So, what happens now?
Well, what happens next is science. The theory makes more concrete, falsifiable predictions. It predicts a tiny gravitational variance, just 0.7%, in entangled systems that we could potentially detect with new ultra-precise quantum clocks. It predicts there should be specific telltale patterns called B-modes hiding in all that data from the cosmic microwave background. These are real clues that labs all over the world can now go hunt for to either prove this theory right or prove it wrong.
And that really brings us to the end of our story for today. This theory completely reframes our picture of the universe. It suggests that space and time, the most fundamental things we know, aren't fundamental at all. They just emerge from a deeper layer of quantum information exchange. And it leaves us with one last profound question to think about. If the entire fabric of reality is woven from information, and if that information has a built-in capacity for self-reference, then what does that make us? What are we, if not a particularly complex and aware pattern in that very same cosmic data stream?